I begin by apologizing for not being able to present this paper in person. I did come to Santa Cruz to attend FOCS. Unfortunately, I tested positive for COVID-19 on the evening of the first day of the conference and had instead to send a YouTube video for my talk. I'll be presenting the paper Fast Numerical Multivariate Multipoint Evaluation. This is joint work with Mrinal and Prahladh, my colleagues at TIFR, Sumanto from CMI, and Simao, who's currently kitesurfing in Brazil. This work is part of a larger paper series. In fact, it's the third and final act of a three-act play conceived, directed, and written by Sumanto Ghosh and Mrinal Kumar. Ramprasad Saptarishi, Simao Herdade, and myself joined the cast of characters for the third act in this series. So these three papers deal with a very fundamental problem in algebra called the multivariate multipoint evaluation problem, or the MME problem for short. So what is the MME problem? The MME problem is specified as follows. Input, there's an underlying field, and this will be of importance to us, as we'll soon see. This field could be any finite field. It could be the rationals, the reals, the complexes. Then there's an ambient dimension. So we're working in the space f to the m. Then we're given a polynomial of individual degree at most d, specified as a list of coefficients. So it's a list of d power m coefficients. And then we are given an arbitrary set of n points in the space f to the m. And the required output in the MME problem is to evaluate this polynomial p on all the n points. So just to make sure we're on the same page, call that the input is the d power m coefficients and the nm field elements required to specify the n points. So we call this combined input d power m plus nm. We denote it by the small n, and that's the input length. And we are interested in algorithms that run fast in this input length. A naive attempt to solve the MME problem would essentially evaluate P sequentially on each of the endpoints. Such an algorithm takes time at least d power m times n, which can be quadratic when d power m and n are approximately of the same magnitude. And our main question, which we would like to answer, is can we do the MME problem significantly faster? In particular, can we solve it in nearly linear time and not run into any, not quadratic as the naive algorithms are? Can we solve the MME problem? In particular, for which fields can we solve the MME problem in nearly linear time? Having thus stated the MME problem, I can give a quick overview of what the three papers in this series actually do solve. The first paper in the series by Vishwas Bhargava, Sumanto Ghosh, Mrinal Kumar, and Chandra Mohapatra solves the MME problem over finite fields of small characteristic. The second paper in the series by Vishwas Bhargava, Sumanto Ghosh, Zayugo, Mrinal Kumar, and Chris Ummans builds on the first paper and solves when the underlying field is finite and has large characteristics. In particular, these two papers together solve the MME problem completely for all finite fields. The third paper in the series, in particular this paper which I'm talking about, deals with the infinite fields, such as the rationals, reals, and complexes. Before we get into a statement of the results proved in this paper, let's look at a brief history of the MME problem. Even though we've been working with infinite fields, let's start with the finite field setting. Particularly, even the simpler case, the univariate case, not multivariate multipoint evaluation, but univariate multipoint evaluation. The most celebrated result here, of course, is the classical fast Fourier transform, which solves the problem when the set of evaluations have a very special structure. particular, they are the roots of unity. Borodin and Monk then extended this algorithm, this classical FFT algorithm, to solve the univariate multipoint evaluation problem when the input is an arbitrary set of endpoints, not necessarily the roots of unity, albeit in the univariate setting. And this was a situation for a very long time. The multivariate case remained open till a breakthrough came from Chris Humans, who showed that when the ambient dimension is not one, but large, but not too large, in fact, it's small, polynomially smaller than the degree, then we do have nearly linear time algorithms for MME for finite fields of small characteristic. Almost immediately after Uman's result, Kedle and Umans extended this algorithm, the same caveat that it worked only for when the ambient dimension was polynomially smaller than the degree, but extended it to all finite fields, not necessarily ones of small characteristic. The key point to note is the Kedle-Umans algorithm is a non-algebraic algorithm in contrast to all the previous algorithms we have seen so far. That's the fast Fourier transform, the Borodin-Monk algorithm, and the Umans algorithm. In what sense is it non-algebraic? An algebraic algorithm is allowed to perform only arithmetic operations on the inputs, particularly currently take the input, add them together, or multiply them together. It cannot perform non-arithmetic operations like writing down the input in some representation, going and looking at the 10th bit of that representation, and so on. Strangely enough, the Kedle-Umans algorithm does such non-kosher, non-arithmetic operations on the input field elements in order to obtain nearly linear time algorithms. Mentioned, this does solve the MME problem for when the ambient dimension is not too large. Notice that an important special case that is left unsolved by this is when the underlying polynomial is actually multilinear. This was resolved by the first paper in the series by Bhargava, Ghosh, Kumar, and Mohapatra, who solved the MME problem completely over all finite fields of small characteristic. Using machinery inspired by Kedle and Umans, the second paper in the series by Bhargava, Ghosh, Duo, Kumar, and Umans extended the algorithm to all finite fields, not necessarily a small characteristic, but any characteristic, but still finite fields. And as expected, this algorithm is a non-algebraic algorithm. So these two papers together resolve the MME problem completely for the finite field setting. What about infinite fields? In particular, the rationals, reals, and complexes. The situation here is complicated due to the bit complexity of the underlying numbers. For example, let's consider the following polynomial. P of x is x to the d, and the evaluation set being the first d integers, 1, 2, 3 up to d. It's not hard to see that the input bit complexity in this case is order d log d, with the output bit complexity is omega d square log d. Given this, one cannot expect nearly linear time algorithms for MME even over integers, forget rationals or reals. So what do we do? So what we do instead to address this, we propose two very natural variants of the MME problem, which take into account the output bit complexity and ask, can we come up with nearly linear time algorithms which take the output bit complexity into account? There are two such variants one can naturally look at. First is the approximate version. Here, we are given, in addition to the usual MME inputs, we are given an extra input, which we'll denote by the parameter t. It's called the approximation or the accuracy parameter. And here, the MME algorithm, the t approximate MME algorithm, is required to output n field elements, b1, b2, bn, which are not necessarily the evaluations, but good enough additive approximations of the evaluations. In particular, it is correct. it's within an additive error of at most 1 over 2 to the t of each of the evaluations. So this is what we call as the t approximate MME. We can similarly consider another version, which is the S exact version. This is for the special case just restricted to the rationals. Here, in addition to the usual MME input, we are given an extra input parameter, which we'll call the output bit complexity parameter S. And this is a promise problem. We have promised that all the numbers, all the inputs, and all the outputs, when expressed as rational numbers, have numerators and denominators whose bit complexity is at most 2 to the S. This is a promise given to us. And given this promise, we want to output all the output rational numbers, P1 by Q1, P2 by Q2, Pn by Qn, so that these rational numbers are in fact the right evaluations. And furthermore, we want to get the representation which is of size at most 2 power s in both the numerator and denominator. So having stated these variants, what do we know about the running time of the best known MME for this problem? Strangely and surprisingly, the univariate case remained open for a very long time, and it was only as recently as 2021 that it was solved by Morose, who gave a solution to the t-approximate univariate multipoint evaluation in time which was nearly linear in n times t. N is the number of input field elements, and t is the approximation parameter. Our main results are an extension of Morose's results to the multivariate setting. In particular, we show that the t-approximate version can be solved, t-approximate MME can be solved in time nearly linear in n times t. Surprisingly, our algorithm, which implies as Morose's result for the univariate case, is not a generalization of Morose's algorithm. Our algorithm is very algebraic and number theoretic, while Morose's algorithm is geometric in nature. In addition to the approximate version, we also solve the S-exact MME in time nearly linear in n times s. This is a statement of the main results proved in our paper. In the remaining 5 minutes or so, I'll give a quick overview of the ingredients that go into our algorithm. So let's begin with try to solve the S-exact MME for rationals. And given the first 2 papers in this series, we'll assume we have nearly linear time algorithms, MME algorithms for prime fields. Given this assumption, there's a very natural algorithm to do the S-exact MME over rationals. So given all the input coefficients and set of evaluation points as rationals, we first clear the denominators and then solve the S-exact MME over integers. Notice this is over integers, not over rationals. While this is a very natural approach to solve the exact MME over rationals, notice the very first step of clearing denominators actually runs into issues. In particular, if all the d power m coefficients were rational numbers whose denominators were distinct primes, then clearing denominators would result in intermediate numbers which are quadratically large in the input length and thus prohibitively expensive for a nearly linear time algorithm. Nevertheless, let us try to ask, can we solve the S-exact integer MME, given that we can solve the MME for prime fields in nearly linear time? And if one is careful, what's the S-exact MME over integers? Here, we are given a bunch of coefficients and evaluation points, all of which are integers, with the promise that all the numbers, every input, and all the outputs are integers of size at most 2 power s. Can we now solve MME? And the idea is basically we can reduce to the prime field case using Chinese remainder theorem. In essence, given the input with this extra promise, we use fast CRT to break it down into MMEs over several different prime fields, solve each of these prime fields independently, and then aggregate the input using reverse fast CRT. And since both CRT and reverse CRT can be done in nearly linear time by standard off-the-shelf algorithms, this together more or less describes how one does the S-exact MME over integers. We then ask, can we use this x-exact MME to solve the t-approximate MME? The s-exact MME was over integers. Like to solve the t-approximate MME over, say, the rationals. And we can. What we'll do is, since we anyway are interested only in approximate this ones, we will truncate each of the given inputs, both the coefficients as well as evaluation points, to k bits after the decimal for sufficiently large k. Since we're anyhow looking for an approximate solution, such a truncation will not cause any issues as long as k is chosen suitably large in terms of the approximation parameter t. Notice that post-truncation, if you write down these numbers as rational numbers, all the numbers have only powers of 2 in their denominators. Hence, we can now do our naive attempt of clearing denominators without causing any blow-up. So we clear denominators and then use the s-exact MME over integers to solve the problem. We just truncate to a large enough accuracy after the decimal point, solve, clear denominators, solve the s-exact MME over integers, and then unscale. This gives us the t-approximate MME. Okay, we still are left with the how to do the s-exact MME. We would like to ask, can we use the t-approximate MME to solve the s-exact MME? And surprisingly, the answer is S. So given the input for the s-exact MME, what we'll do is we'll pretend as if we are actually trying to solve the approximate problem and get good rational approximations of the answers, very good rational approximations, and use the fact that there are extremely good rational number reconstructions. That is, given an unknown rational number and a good enough rational approximation to it, we can actually construct the rational number from it. And this basically uses, we construct these fast rational number reconstructions, which in turn use fast GCD algorithms. Putting these together, we thus reduce the s-exact MME to t-approximate MME. This more or less brings me to the end of the talk. So a quick summary, we consider the MME problem over infinite fields such as the rationals and reals, and gave nearly linear time algorithms in both the approximate and exact settings. While that resolves the MME questions for most fields of interest, there's still a few lingering questions which we hope will be addressed shortly. There's this question of algebraic versus non-algebraic algorithms. What about other fields? Any applications? Okay. Thank you.